So in this video, we're going to continue on with the discussion on capacitor applications, but we're going to focus more on where these capacitors would go and then what would be the best sizes based on these locations. And so where in the last lecture, we were more concerned about the operational aspects when the capacitors would be switched on. We're going to be more concerned in this lecture on the planning aspects as far as locations. And what I'll do in the first part is I'll give you a little bit of background on some of the math behind this, and so you can kind of see how we look at capacitor placement from a loss reduction and a voltage drop standpoint. And then to explain this, we're going to use this concept of VAR profiles. I guess more properly that would be called VAR-mile profiles. Also, in the first part, I'll talk about a very common rule that's used for capacitor placement called the 2/3 rule. And then in the second part, I'll talk about an update to this rule called the half kVAR rule, which is probably a little bit more practical for real distribution circuits. And then I'll show you a windmill example as far as the different sort of placements and what kind of impact the different placements would have. Finally, I'm going to wrap up in the second part talking about capacitor costs and what actually kind of goes into this when we put a capacitor in the field. In the last part, in part C, I'm going to talk a little bit about the economics of capacitor placement. And it's not just for capacitor placement. I mean, it's really the economics for any sort of improvement we would make on a distribution circuit. And I'm going to introduce this concept of a fixed charge rate, show how it would be calculated. I'm not going to go into a lot of detail, but I'm going to show you the steps and then show how this would actually then get applied for an actual problem then. Okay, so let's just kind of talk about ideally what do we want to do with capacitor replacement. Let's suppose I had a circuit, and what I have is I've got two different loads. I've got a load that's P1 plus JQ1 at bus 1. And I've got a load P2 plus JQ2 at bus 2. And so at the top of the feeder, what we're trying to do is we're trying to get this power factor as close to 1 as possible. So if I were going to put capacitors in the circuit and I had every conceivable size of capacitor available to me, what would I want to do? Well, actually, what I would want to do is I would want to put a capacitor at bus number 2, where this particular capacitor, let's call this QC2, was going to have a value given by minus Q2. And then I'm going to have a value at bus number 1, which is going to be QC1, which is going to be equal to minus Q1. And so what would happen in this case is I would get exact cancellation. I'd be basically making those loads look like they're both at unity power factor. Now, we could fine tune this a little bit because I'm still going to have on my feeder, I'm still going to have an amount of loss, I guess I'm going to call it that, that's going to be given by this current IS1 squared times X1. And I'm also going to have a magnetizing loss that's going to be I12 squared times X2. And what this corresponds to is the fact that since these lines, overhead lines or cables, have a series impedance, then there's going to have to be some magnetizing power that's going to be required to set up the magnetic fields associated with those lines. And so if we don't want that supplied by the transmission grid, then what we may actually want to do is maybe have half of this value that gets supplied by this capacitor, and maybe half this value gets supplied by this capacitor, and then maybe half or this total value could get supplied by this capacitor as well. So we might want to actually increase the amount of reactive power output at bus number 1 and 2 so we can apply the line Q as well. All right. Usually that I squared X is not going to be near as large as the load Q. And so if we could at least compensate locally at the loads, we'd actually be doing pretty good. But there's a lot of issues associated with doing something like this. So ideally, if we had any possible size of capacitance available to us, what we'd be doing is we'd be doing power factor correction at all the different loads, right? But the thing we run into on this is that it gets very difficult to do it, because if we were going to do something like this, then we would have to have adjustable capacitors, because actually with time, this load Q is going to be changing, right? And so that makes it a little bit difficult to do that unity power factor correction at loads where the loads aren't going to be constant, right? So how are we going to adjust this capacitance? That would be very, very difficult to do. And so obviously we want to kind of eliminate pushing too many VARs across these lines, because as we're going to see in a little bit, VARs don't really travel that well, over lines. The problem is if I'm going to push VARs over the line, it's going to give me some additional voltage drop. But the issue you run into with trying to do this unity power factor correction of all the different loads is we would have to have VARs that would be continuously adjustable as load changes, right? So that's going to be kind of expensive if we did something like that. If we simply use a bunch of small capacitor banks and put them in some type of a switch arrangement, this would be kind of costly as well. You have to have too many switches out there switching in these small banks in and out all the time. We could maybe do this with some type of a solid state device, power electronic device, where we have a, say, inverter-based generation, and we maybe can inject VARs at different levels. But to do something like that is much, much more expensive than using the capacitor bank. And so we have to be kind of realistic here and probably go with a few locations of capacitor banks instead of trying to adjust VARs at every bus in the circuit. And so when we talk about this problem, it's going to be useful to kind of focus on what I've referred to as a feeder VAR profile, or I guess you can call it a VAR-mile profile, where if I had a feeder and if I had different buses on this feeder, then if I took a sensor, let's say if I had a reactive power sensor, as I move down the feeder from the top of the feeder to the bottom of the feeder, how would that Q I measure change as a function of position? And so this is kind of the miles part. This would be the miles from the substation. And then what we're interested in knowing is, well, how does that Q measurement change as a function of position up and down the feeder? And what we're going to see in just a little bit is that we're going to have some losses. We're going to have some losses. We're going to have some voltage drop that's going to depend on the real power. And this isn't anything we could change with the capacitor bank. A capacitor bank just impacts the reactive power flow. And so what we're going to see is there's going to be at least some losses we're going to have to live with due to the real power requirements of loads. There's going to have to be some voltage drop components we're going to have to live with just due to the real power of the load. And so if we're going to make any changes to this, and kind of improve our situation, then any change in losses or any change in voltage is going to have to be accomplished via capacitors, because we've got to serve the load. We can't monkey around with that. And so if we're going to make any improvements to the circuit, we're going to have to do this through capacitor placement. And what I'm going to claim here is, if I'm going to improve things and if I'm going to lower losses, I'm going to improve the voltage profile, what I need to do is I need to minimize the area under this VAR profile curve. And so if I have a VAR profile curve where I take Q as a function of distance down the line, if it looks something like this, what I want to do is I want to keep this net area as small as I can. So let's take a look at some of the math behind this. We'll take a look at the math on the losses first. And the way we're going to do this to start off with is we'll just kind of take a look at this 2-bus circuit. And let's suppose we're just doing VAR compensation at bus number 1. All right, so each of these loads has a real and a reactive component to it. And if I wanted to estimate this particular current here at IS1, you know, one way I could do that is just simply take the complex conjugate of the power and divide that through by a voltage, right? Now I'm going to make an approximation here. This voltage profile is going to be relatively constant. And so I'm just going to divide this through by nominal voltage. And then given that I could ignore line reactance, the I squared X type of component, then basically what I'm going to have at IS1 is going to be a current that's going to relate to the total P and the total Q below that point, where the net Q is going to be the net load Q, Q1 plus Q2, minus QC1, which is the compensation I'm going to have at bus number 1. All right, so that's going to be my value for IS1. You can see I can adjust this by playing around with this value for the QC1. Now, if I want to get losses, then I need to have an I squared R type of a value. And so if I take IS1 times its complex conjugate, I get this form for the losses. And we've kind of seen this before in some class examples and homework. And then the net loss is going to be I squared R for both of these line segments. So the first line segment I can improve upon. All right, I can basically kind of adjust what this effect's going to be. Although what I'm going to have for the second line segment here is not anything that's going to be impacted by that compensating capacitance, because that would only happen if I had some capacitance at bus number 2. What you can do if you have this expression, right here for losses in terms of P and in terms of Q, you could break that into 2 parts. You can break that into the part associated with P, you can break that into the part associated with Q. And you can see here that this part associated with P isn't anything I can do anything about. It's just, you know, it's just because of the way we have our circuit set up. It has due to line resistance and reacting with the real part of the load. However, if you look at this second part here, this is something I can change. I basically have the ability of changing that value. In fact, I can actually make that value 0. All right. So you can see that by changing QC1, if I can get that to cancel out with Q1 and Q2, then what I could actually do is I could actually reduce losses, right? So note there is a certain minimum value for losses. I can't set losses obviously to 0. I'm going to have some minimal loss. However, what I can do to a certain extent, if I compensate properly, I can at least minimize the losses. But what you have to watch out for is if we overcompensate, if we put too much capacitive compensation in there, the losses actually go up again. And so there's sort of like a sweet spot where if you're going to look at the value for QC, that there's some point above which if you add too much capacitance, the losses start to go up again. All right, and that's what you have to watch out for. Now, as far as voltage drop, if we take a look at our K-factor approximation, if we just do this in terms of the load currents and the line currents, what we're going to have for the voltage drop across this first segment, for example, is R1 plus JX1 times the complex current going through that line. That's going to be equal to the voltage drop. And if I assume that the imaginary part of this is 0, if I just take a look at the real part's R1 times IDS1. This is the real part of that line current minus X1 times the imaginary part of the line current. Keeping in mind that if I have a lagging power factor load, that IQ is going to be negative. All right, so actually we get voltage drop due to both the line resistance and also the line reactance. And IC is going to be positive. And so if I do something similar to the previous slide, where now I focus on looking at, say, what V2 is, well, that's going to be the source voltage minus the drop across the first line segment minus the drop across the second line segment. And so if I set this up in terms of the load current, the real and imaginary parts of the load current, I see something similar again, where I have a voltage drop component that can be adjusted through using different sides of that compensating capacitance. And what's interesting about this particular case is that I can arbitrarily increase the voltage to anything I want to by just simply using larger and larger values of capacitance. And so there's not any limits to how I can get a voltage rise in this particular circuit if that's what I so desire. So there's going to be a voltage drop component, which is going to be constant due to the resistive load. And then there's going to be a drop component that's going to be a function of VAR flow. And I can actually raise or lower the voltage if I want to by adjusting the size of this capacitance. Now, the thing you have to watch out for is if I'm overcompensating and I'm putting a lot of Q in there in order to push voltage up, I'm going to be sacrificing my performance in terms of losses. I'm going to make the losses go up. So to some degree, I can do voltage control with capacitors, but I'm going to pay for it in terms of increased losses, which was why we only take it to a certain point. So anyway, I can get any sort of voltage rise I want, but in reality, I'm not going to want to push that too much. And another thing that's going to limit me too is I'm still limited by having these fixed capacitor sizes. So I'm going to have jumps in voltage as I turn capacitors on and off. So let's take a look at a sample circuit. I think it'll make this a little bit clearer if we just kind of go through some examples. And this is a 12.47 kV circuit, and I have a line positive sequence value per mile. So this is 6 miles long, and each of these segments is just simply 1 mile in length. I'm regulating the voltage at the top of the feeder to 1.05 per unit, and I've got a net load of 5100 kVA at a power factor of 0.707. So power factor 0.707 means I have as much Q as I have real power for each of these different loads. And what I'm going to do is I'm still going to break this 5100 kVA where each load is going to have the same value. And what I'm trying to approximate here is I'm trying to approximate kind of a uniformly distributed type of load. So what's the VAR profile for this circuit going to look like? And let's just neglect the I squared X line in this case. So if I've got 5100 kVA load, and if I multiply by the reactive power factor, which is the sine of the arc cosine of 0.707, then what I'm going to get for the total kVAR needed is going to be 3600 kVAR. All right, I'm going to need 3600 kVAR. So at the top of the feeder, what I'm going to need is 3600 kVAR. Now, as I go past each node, this amount drops until finally when I get to the end of the feeder, then I don't have any more line kVAR anymore. It just simply goes to zero, right? And so between each set of nodes on here, I just put a straight line. It doesn't actually go on the straight line if you took the real measurement out there, but for the sake of explaining it, it's just easier if I just kind of use a straight line fit between each node point. And so I start out at the top of the feeder, 3600 kVAR, need to supply all the loads. And as I go past each load, this drops off, drops off, drops off, until I get to the very end of the feeder, and I get right past that last node point, and I don't have any kVAR flow anymore. So if you're going to analyze this circuit, we could use K-factor analysis for something like that. What we're going to see is as we go from the top of the feeder down to the bottom of the feeder, the voltage drops off as shown. We get a lot of voltage drop across the first segment because it has the most flow. The voltage drop tapers off, and by the time we get to the end of the feeder, we've got 0.94 per unit volts. The net losses in this case, if you looked at each line segment, is going to be 250 kilowatts. And so this is kind of a base case here where we're not doing any power factor correction. All our VARs, all our kVARs are coming from the substation, from the transmission system. So if we look at the VAR-mile profile, we could see that there's a lot of area under this curve. And I don't have, as a result, very good performance associated with this because I'm basically having to push VARs all the way from the substation all the way down to all my loads. So anyway, I'll give you guys this copy of the spreadsheet that I'm using for these calculations, but what I can do in this case is I can actually put different values for kVAR, each of the different buses in the circuit. And then what this is going to do is it's going to calculate the voltage drop across each segment and also calculate the losses across each segment. And so this is how I'm getting the numbers, is I got this spreadsheet set up to do K-factor analysis on this particular 6-bus circuit. So let's look at another scenario. Let's suppose I'm going to put a power factor correction capacitor out here, and I'm going to put 1800 kVAR, which is half what I need. I'm going to put that at the midpoint. So how much do I have to draw now from my substation? Well, if I got 1800 at the midpoint, then 1800 kVAR is all I need from the substation. If I took this measurement, it's going to drop off, drop off, drop off, drop off. And then once I get right past that bus 3, then what's going to happen is I'm going to be using the 1800 kVAR from that capacitor to supply the rest of the kVAR load for the rest of the circuit for the last 3 miles, right? And so if I look at my performance for my voltage, now it only drops down to 0.967, and my losses turn out to decrease to 164 kW. So it's actually a pretty impressive improvement. Not only do I reduce the losses, but I increase the end of the feeder voltage as well. And the difference here could be seen by looking at the change in the kVAR profile. Because if I look at the area under this curve compared to the area under this VAR profile curve, you could see that there's less area associated with this. And because I'm cutting down on the peak Q, I'm reducing this from 3600 down to 1800. Since the losses are related to Q squared, then basically what's happening in this case is I'm able to improve the performance of the circuit. By cutting down on Q flow, I not only reduce the voltage drop, but I reduce losses as well. So what I'm doing in this case, what you should be seeing is I'm basically compressing this VAR-mile profile down. I'm squashing it down. And so by putting that capacitor at the midpoint, by compressing this, I'm getting better performance. Now let's look at another location. Let's take that same capacitor, that 800 kVAR capacitor, let's put that at bus number 4. So what's going to happen in this particular case? Well, I still need to have 1800 kVAR come from the substation. But now what's going to happen is what I'm going to have in this particular case is if I put this capacitor at bus number 4, I'm going to have 1200 kVAR go to the right, and I'm going to have 600 kVAR go to the left, right? And so now that capacitor is pushing VARs in 2 directions now. It's actually sending some of that VAR upstream. And what's happening now is if you look at the area, well, now I've got some negative area, and that negative area is going to kind of cancel out a little bit with the positive area. And I still even have a little bit more compression in this case. And so I go from 164 to 151 kilowatts of losses. And the voltage profile is still a little bit better. And so what you see is that I had the same size of capacitor, but just based on the location I put that capacitor at, I can still get some further improvement. So position makes a difference. And again, you could see that I'm still continuously to squash or compress this VAR-mile profile down. All right. So I could try another placement strategy. I could have 2,700 kVARs now. And what I'm going to do instead is I'm going to put that at bus number 3. Now what's going to happen? Well, I'm going to have 1,800 kVAR go down. I'm going to have 900 kVARs go up toward the substation. Again, I'm going to get some changes in the VAR profile. If I look at this net area where this is actually going to be kind of like a negative area in this case. And what I'm still continuing to do in this case is I'm still continuing to kind of compress this further. And so the losses go from 151 to 148, and then the voltage, the low voltage in the feeder goes down to 0.98. So this is actually the best result I have yet. But you see, I'm starting to hit some diminishing returns. The improvements aren't as really great now. So I'm hitting some diminishing returns as far as what kind of improvement I'm actually getting to this case. But anyway, what we want to do is we want to have a strategy that compresses that VAR profile as much as we can. We want to basically kind of, in a way, find a situation where we get these areas, these positive and these negative areas to kind of cancel out. That would correspond to the maximum squashing, the maximum compression effect. All right, so what would be a rule or a guideline for this? Well, people have been kind of looking at this for a long time. I mean, this goes back, probably like 80 years, people have been kind of looking at this. And there's a rule that they came up with. It's called the 2/3 rule. And so the idea would be that if we want to have an optimal capacitor size and an optimal location, the way we're going to do something like this, and if we just have one capacitor, is we're going to size a capacitor where I've got 2/3 of the VAR requirements for the circuit. And if I have a uniformly distributed load, the best location for this is going to be 2/3 of the way down the line. So this is dependent on the fact that as I go down the feeder, basically each of the loads are basically the same size. All right, that's what this is based on. And so what happens is that the substation sources can provide 1/3 of the net VARs for the load, and that capacitor bank is going to provide 2/3 of the VARs. So if I look at the 2/3 rule, if I have 3,600 kVARs that are required, 2/3 of the 3,600 is 2,400 kVAR. What I'm going to do is I'm going to take that 2,400 kVAR and I'm going to put that 2/3 of the way down the circuit, which is at bus number 4. So now I'm going to have the substation provide 1/3 of the net VARs required for the circuit. That's 1,200. I'm going to have this capacitor bank provide 2,400. And now look what happens to this VAR profile. We're getting to a situation where I'm getting pretty good cancellation between the positive and the negative parts, as far as the area calculations. And for one capacitor, this would be the best compression I could actually get. And so in this case, I get the losses actually down to 140, and the voltage at the end of the feeder is 0.987. And so this would actually be the best results I could get for this particular scenario. Thing to keep in mind in this case is this particular 2/3 rule is designed to minimize losses. It doesn't always guarantee the best voltage profile. It just kind of worked out in this case. But if you just had this uniformly distributed load, then this is the best you can do as far as capacitors. And so this you'll see in planning manuals for a lot of utilities. A lot of utilities are actually set up where they make use of this 2/3 rule. And this is why you see these capacitor bank locations that tend to be more at this mark on the feeder. If you just do one capacitor, then you're going to size it for 2/3 of the total net reactive power characteristic, reactive power required, and then you're going to put that at the 2/3 location. Now you can generalize this, and you can do this for 2 capacitors or 3 capacitors or 4 capacitors. If this is going to be the case, and the size of each capacitor is going to be 2 divided by 2n plus 1, where n's the number of capacitors, and you're going to have to put this at distances where each distance location is going to be 2 divided by 2n plus 1. And so let's suppose you had like 3 capacitors you want to put on a circuit. Then you size each of these where this is going to be 2/7 of the total VARs needed. So you have 3 equal sized capacitors, and these are going to be at locations 2/7, 4/7, or 6/7 of the line length, starting at the substation. The problem you run into with this generalized 2/3 rule is it's rather difficult to apply in practice. Because if you're talking about having multiple capacitors, first of all, this is going to be more expensive to put multiple capacitors out there. The other thing is you might not have access to these locations on the feeder. And then you'd have all these weird size values that you would have to have for these capacitor values. And so I don't really see where a lot of utilities would make use of this generalized 2/3 rule. They might make use of the 2/3 rule. But this generalized 2/3 rule is a little bit difficult to apply in practice. And so what actually has been developed instead is what we're going to call a half kVAR rule, which we're going to go into a little bit. And so anyway, this is some of these VAR-mile profile curves from a book by Lee Willis. Lee Willis wrote a book on power system planning, distribution planning, where he has a lot of curves like this. And he kind of shows what the VAR-mile profile would look like if you had a situation where you had just one capacitor in the circuit. But then if you have like 2 capacitors in this idealistic situation, it kind of shows how the VAR profile gets compressed even further. And then if you have the situation where you have 3 capacitor banks, you can get even more of a reduction. But again, the problem you run into is for a real circuit, it'd be kind of hard to get these capacitor sizes and have availability to these locations. And so anyway, as I mentioned before, what we would actually be using in a realistic circuit, if I were looking at multiple capacitors, is this half kVAR rule, which we'll get into the next video segment.